The heat wave is breaking. After weeks of a stagnant heat dome trapping hot, humid air over more than 200 million Americans, and a parallel dome baking Ontario and Quebec at the same time, the pattern is finally giving way. But what is moving in to replace that heat is not a gentle cool down. It is a violent convective outbreak so intense that meteorologists monitoring live radar and satellite feeds say the maps are now displaying colors many of them have genuinely never seen appear across this large an area before. To understand what that actually means, you first need to understand how meteorologists visualize storm intensity. Radar and satellite maps use color gradients to represent measurable physical thresholds: rainfall rate, hail core size, wind shear, and cloud top temperature. Green usually means light activity. Yellow and orange indicate moderate intensity. Red signals a serious, potentially dangerous storm. And beyond red, reserved for the rarest, most violent convective cells, sits a narrow band of deep purple, magenta, or near black shading that most viewers never actually see illuminated on their screen, because most storms, even severe ones, never generate readings extreme enough to trigger it. This week, across a wide swath of the eastern United States and southeastern Canada, that rarest shading lit up repeatedly in multiple separate storm cells over a period of several days. That is the part meteorologists describing this event keep returning to. Not that one storm was unusually violent, but that so many storm cells reached that same extreme threshold within such a tight geographic and time window. Here's how we got here. A massive heat dome, a large area of high pressure stalling in the upper atmosphere and trapping warm air beneath it like a lid, settled over the eastern two-thirds of the United States in late June and held firm into early July. Heat index values climbed close to 110 degrees Fahrenheit across huge portions of the country, and high humidity kept overnight temperatures from dropping much below the mid-70s in many areas, giving people's bodies little chance to recover between consecutive days of extreme heat. Atlantic City, New Jersey, hit 106 degrees Fahrenheit on Independence Day itself, one of dozens of temperature records tied or broken across the country during the peak of the event. At the same time, just across the border, a nearly identical heat dome settled over southern Ontario and Quebec, pushing humidex values into the low 40s Celsius and putting millions of Canadians under extreme heat warnings. Both domes were, in essence, the same broader atmospheric pattern expressing itself on both sides of an international border, trapping enormous amounts of heat and moisture beneath a lid that could not hold indefinitely. When a heat dome like this finally breaks, it typically does not do so quietly. Severe weather is common along the northern and eastern edges of a heat dome, precisely because that is where the boundary between the trapped hot air and the approaching cooler system creates the sharpest atmospheric contrast, the exact ingredient severe thunderstorms feed on. This year, that boundary produced results that stunned even experienced meteorologists. In Ottawa, on Canada Day itself, rounds of severe thunderstorms tore through the region for roughly 4 hours, dumping 118 millimeters of rain at the airport alone. To put that number in context, the previous record for rainfall on that specific date at that location stood at just under 59 millimeters, meaning this year's storm did not simply break the record, it roughly doubled it. A meteorologist with Environment Canada described how rapidly the storm intensified, saying the rain began falling fast around 2 in the afternoon before becoming significantly heavier by 3, illustrating exactly the kind of explosive, short-fuse convective development that has become the hallmark of these heat dome breakdowns. The damage that followed was severe and immediate. Roughly 170,000 customers lost power across the province of Ontario by early evening. Ottawa's own municipal utility reported tens of thousands of additional outages within the capital region itself. Hazardous conditions forced the cancellation of the National Capital, region's Canada Day evening festivities entirely, including the fireworks display, with organizers stating plainly that public safety could not be compromised. Basements across the city flooded, trees and power lines came down under damaging wind gusts, and Toronto's Pearson Airport recorded a wind gust of over 100 kilometers per hour as the storm system tore through the wider region. Local meteorologists later described it as one of the worst storms the area had experienced in the past 25 years. Just south of the border, the storm systems that finally broke the American heat dome proved equally destructive. Over several days in early July, multiple rounds of severe thunderstorms swept across the country, ultimately triggering more than 1.3 million power outages and contributing to 4 fatalities. Among the most striking, individual data points to emerge from this outbreak. Meteorologists confirmed that the storms responsible for breaking the heat wave also produced what is now believed to be the largest hailstone ever recorded in the state of Connecticut, a genuinely historic marker for a single storm system to leave behind. If content like this, the kind of overlooked connection between a record heat wave and the record-breaking storm violence that follows it, is something you want more of, go ahead and like and subscribe so you catch the next one. because this pattern of extreme heat giving way to extreme convection is becoming one of the defining features of how modern summers actually unfold. Tornado risk also became a genuine concern during portions of this outbreak, since the same wind shear and instability that fuels large hail and damaging straight-line winds can, under the right conditions, organize into rotating supercell thunderstorms capable of producing tornadoes. Several states under the path of these storms saw tornado watches issued alongside severe thunderstorm warnings, requiring residents to monitor multiple simultaneous threats: flash flooding, large hail, damaging winds, and the possibility of tornado development, all stemming from the same underlying weather system within a matter of hours. Health systems across the region faced their own version of this compressed transition. Hospitals that had spent weeks treating heat-related illness, heat stroke, dehydration, and cardiac complications worsened by extreme temperatures suddenly had to pivot towards storm-related injuries, carbon monoxide poisoning cases from residents improperly running generators during extended power outages, and the general strain that comes with treating patients in facilities that may themselves have lost power or backup systems during the outage. Public health officials in several jurisdictions specifically warned residents about generator safety in the days following the storm, noting that carbon monoxide poisoning incidents tend to spike predictably whenever a severe weather event knocks out power for an extended period during hot, humid weather. What makes meteorologists particularly uneasy about this specific breakdown is the underlying physics driving it, and it is not complicated to explain, even if the consequences are genuinely alarming. A warmer atmosphere holds substantially more water vapor than a cooler one, roughly 7% more for every additional degree Celsius of warming. That extra atmospheric moisture does not simply sit there waiting quietly. It becomes available fuel the moment conditions align for a storm to form, meaning that when a heat dome this intense finally does break down, the resulting convection has access to a larger reservoir of stored energy and moisture than it would have had decades ago under a cooler baseline climate. Researchers studying long-term rainfall intensity trends across North America have found consistent evidence supporting exactly this mechanism. Climate scientists analyzing decades of hourly precipitation data across major cities have documented a clear upward trend in how much rain falls during the most intense bursts of any given storm, even in cities where total annual rainfall has not changed dramatically. The distribution is shifting toward more extreme, more concentrated bursts of rainfall packed into shorter windows of time, exactly the pattern that produced Ottawa's doubled rainfall record and the flash flooding that followed. There's also a structural reason these storms are becoming harder to forecast with the same lead time meteorologists once relied on. Traditional severe weather forecasting depends heavily on identifying broad atmospheric setups days in advance, and then narrowing down timing and location as the event approaches. But the kind of explosive, localized convection seen this week, where a storm cell can develop from essentially nothing into a record-breaking rainfall event within a couple of hours, compresses that forecasting window dramatically. Meteorologists increasingly rely on rapid update radar and short-term nowcasting tools, specifically because the older multi-day forecasting approach simply cannot keep pace with storms that intensify this quickly. The heat dome breakdown was not confined to just this one event either. It followed a now familiar seasonal pattern where extreme, prolonged heat builds enormous atmospheric energy over an extended period, and that energy gets released in a short, violent burst once the blocking pattern finally collapses, rather than dissipating gradually the way older, more historically typical weather transitions used to unfold. Forecasters tracking this year's broader pattern note that record heat returned to parts of the affected region, again roughly 2 weeks later, when temperatures once more approached the upper 90s Fahrenheit in several cities, suggesting the underlying atmospheric setup driving these extreme swings has not fully resolved even after this particular breakdown event. Looking ahead, forecasters caution that this particular heat dome breakdown does not necessarily mark the end of extreme weather risk for the rest of the summer season. Long-range forecast models tracked by multiple national meteorological agencies continue to show elevated potential for renewed high-pressure ridging and additional heat building later in the season, meaning the same fundamental setup: extreme heat, accumulating atmospheric energy that eventually has to release itself violently, remains a live possibility rather than a one-time event already fully in the past. Utility companies across Ontario, Quebec, and multiple American states have had to rapidly pivot crews and resources from heat-related emergency response, cooling centers, medical support for heat illness, directly into storm damage assessment and power restoration work, sometimes within the same 48-hour window. Officials describe this compressed transition between fundamentally different types of extreme weather emergency as one of the more difficult aspects of managing a modern, severe weather season, since the staffing, equipment, and public communication needed for one crisis type looks completely different from what the very next crisis requires. Researchers who study public risk perception note an important psychological dimension to this pattern as well. Because heat waves develop gradually and receive days of advance warning, the public generally has precautionary action. Severe convective storms, by contrast, often develop and intensify within hours, giving residents far less time to psychologically process the shift from heat safety concerns to storm safety concerns. Several public safety officials have specifically cited this compressed cognitive transition from thinking about heat risk to suddenly needing to think about flash flooding, hail, and wind risk as a genuine communication challenge that traditional weather safety campaigns were not originally designed to address. The broader takeaway that meteorologists keep returning to across every interview and analysis published in the days following this outbreak is remarkably consistent regardless of which specific agency or research institution is doing the talking. Extreme heat and extreme convective storms are no longer best understood as separate categories of summer weather risk. They are increasingly two phases of the same underlying atmospheric event, connected by the same reservoir of stored energy and moisture that builds during the heat phase and then releases, often violently, once the blocking pattern responsible for that heat finally breaks down. Understanding that connection, researchers argue, is essential not just for meteorologists refining their forecasting models, but for ordinary residents deciding how seriously to take the days that follow whenever their region finally sees a stubborn heat dome begin to weaken. So the next time you hear that a heat warning has ended, do not treat it as the finish line of a summer weather story. Increasingly, it is closer to the halfway point, the moment when one kind of danger gives way almost immediately to another, arriving with maps lit up in colors that, this year, across this much territory, meteorologists say they simply had not expected to see so early in the season. Whether the rest of this summer brings more of the same is something forecasters say only time, and the next radar update will tell.